Up and running again. All right, so this is more calculus for the Algebra 1 student. Now we're going to plant some seeds so that when you do get to a formal calculus class, you got some idea of what the study's about. Again, I'm not a big fan of sequential instruction. I don't think that you necessarily have the time to see patterns, to consider the conceptual ramifications of what you're doing. So I like to, as I say, plant some seeds. So one of the seeds I want to plant is how are functions changing? Very important. Linear functions increase or decrease, or they can be in between. Quadratics decrease and increase when the a value of the quadratic is positive. Cubics are a little bit more complicated, but we have increasing, decreasing, increasing situations there. Sometimes cubics just increase, sometimes they decrease. But the real question is, how are they changing? Well, why is that important? We got a major topic in front of us right now. Some people say it's an existential crisis, climate change. And I think it's very important to get a sense of how things are changing over time, because you can project into the future. And those projections at the moment aren't that pleasant, right? But it's important to follow the science. At least some of the deniers of climate change have come around to recognize that we have an issue here and it needs solving. All right, so let's start talking about change. Let's just look at some change. Quadratic change. It's one of the functions that's easiest to kind of grasp. I think most people have a feeling for what a square looks like. And the squaring process it's not rocket science. So we can look at minus 3.001 squared without a calculator. I hope that if you check it, it's 9.006001. And minus 3 squared is 9. So what can we say? Well, it sure looks like squaring produces positive numbers here. I think that's true. And it looks like negative 3.001 to negative 3, my x's are actually getting bigger, even though the magnitude, is certainly bigger on the left, but negative 3 technically is a bigger number than negative 3.001. So we can read from left to right. And as we read from left to right, the area is coming down. And I think we have a feeling for that. Right, so negative 3.9 is on the left side of x squared, that function, right? And it looks like reading left to right, we're decreasing and then increasing. And I can see now the numerical, I can see the geometric representation. They don't look like very good squares that are being drawn here. My apologies. But numerically, yeah, things are going down. And then I guess the question is, at what rate? Well, I've collected a table of values over there, so we'll look at that momentarily as I move down the wall. Somebody took my science card. Very disappointed, because now I had to pick up the computer and move to the left. But let's continue with this process. Negative 2.001, negative 2.001 squared is 4.004001. And negative 2 times negative 2 is 4. Still going down. But it looks like the change here is not as big a change as what we were looking at before. So we're going to analyze that in a table of values in just a moment. And negative 1.001 times negative 1.001, I couldn't fit the 6 decimals inside there. So I wrote 1.002001 without a calculator. I hope that's still true. And negative 1 times negative 1 is 1. So it looks like there's some change to 1.0003 decimal places. Yeah, it's coming down. And then negative 0.001 times negative 0.001 gets me still a positive number, but 6 decimal places with a 1. It's pretty small change. And I couldn't draw the square, so 0 times 0 is 0. Those first 3 decimal places suggest that it's not changing much. So we look at all those table values and we put them in one place so we can do some critical thinking. Yep, from negative 3.001 to negative 3, the area went down 0.006. Then it went down 0.004, down 0.002, and then it's 0. I wonder if there's a pattern there. What if there's something where this number turns into that number and this number turns into that number? I guess there is. Sure looks like we're doubling those numbers. And what were those numbers? Negative 3. If I'm not mistaken, negative 3 was the length of that particular square root. And I guess if we have, well, let's go to the positive side of things. Because I think, there's a symmetric side to x squared. Right? I mean, first off, we were looking at going down at 6 to 1, then going down at 4 to 1, and then going down at 2 to 1, and then no change. And it sure looks like on the other side, if we did the symmetric 3 gets you 9, 3.001 gets you 9.006001. Things look like they're getting bigger at 6 to 1. And I bet 4 to 1. And I bet 2 to 1. And I bet 0 to 1. Yes, and I think we can kind of see that as we go from left to right, that symmetry of change. And I don't think I'm doing anything spectacularly difficult. All I think I'm doing here is y2 minus y1 and comparing it to x2 minus x1. We do that at algebra 1. I'm just doing it over a small interval. And it gives me a little sense of the full picture: down 6, down 4, down 2, 0, up 2 to 1, up 4 to 1, up 6 to 1. Oh, yes, I'm starting to dive into the quadratic a little more deeply. And it sure seems like it has something to do with this area increases when I increase a dimension. And if I want it to be a square, I better increase that dimension as well. And then I just draw a little bit of a layer of area on top of what was already square area. And that is the accumulation process. And if I standardize this change in the dimension of the square and pretend that in a split second, no matter the size of the square, I think I'm really measuring the amount of ink I'm putting on the board with respect to some standardized change in x, whether it be time or something else. Okay, so let's continue on. Let's see where it takes us. Let's establish some things. We have an x that gets us a constant, and then on the other side we have a symmetric one. And it sure seems like, and this is for a values greater than 0 in the ax squared plus bx plus c. I'm only talking about cup shape up, trying to keep it as simple as possible. But it sure seems like this is split right down the middle. So if I add x1 and x2 up and divide by 2, or x3, excuse me, I think I get the input that gives me, in this case, a minimum. Well, let's dive into that a little more with an example. So what do we do when we put things in graphic form? Well, we actually find this value. And I'm going to talk about minus b over 2a in a little more detail here at the end of the video. But if we did, 20 divided by 4 gets us 5. And then we could write, that 5. This has area, right? That square has area. How do I minimize that area? Well, geometrically, I guess I did it on the side. Okay, you can kind of see that. But let me stick with this for a moment. Okay. When did we get a minimum from the squaring process? And I'm going to double this, subtract 43, this is squaring process. When did we get the minimum? Well, we did it over there when there was no area, right? If there's no area, then the rate of change is, it's zero, right? So at this instant, that slope is zero. And why? No square area. You start squaring numbers, you get positive results except for one square, and that's the zero square. And this has a minimum. It's cup-shaped up, and it appears to be happening at 5. So 5 has to act like a 0, and that's one of the reasons we write x minus 5 squared. All right, so back to this drawing. So here's area. Right, how do I minimize this area? Well, let me start taking some of the layers away. Okay, I hope you can see I'm taking an x away and another x away. And it keeps maintaining that shape. And pretty soon I'm getting down to how much area? No, I'm minimizing by getting to 0. And that really is a concept of a limiting process. And you're going to study that in calculus. The smallest area I can make is 0 for real numbers. Okay, now let's look at the squaring of x minus 5 over here. So what makes this 0? Well, first off, let's just see that x times x is x squared minus 5 times, I should put the x minus 5 here for right now. X minus 5, right? Minus 5 times x is minus 5x, minus 5 times x is minus 5x, minus 5 times minus 5 is 25. All right, so what happens if I double the x squared? I get 2x squared. Did I write? Oh yeah, I wrote it here. So if I double the x squared, I get 2x squared, minus 5 is minus 10. If I double it, I get minus 20. Doubling 25 gets me 50, and 50 minus 43 gets me 7. That's in graphing form here. Okay, but let's put 5 in. That's supposedly the most important number, so let's put 5 in. Okay. Well, I know what 5 times 5 is. It's 25. And 5 times minus 5 is minus 20. And remember, this 25 is constant. We'll call it K. Okay? And minus 5 times 5 is another minus 25. Well, I've been telling you the first two terms are coming to you in a 2 to 1 and opposite sign process. That's a pattern you see at the vertex, and it's the only time you see that. Why? Because we're making 0 out of this area. Remember, that was 25 as well. 50 minus 50, no area. That's a minimum. Because anytime you put another number in here, that area is going up. But there's also this pattern of 2 to 1. So let's put 5 in and see it. 5 squared times 2, 50. Minus 20 times 5, minus 100. Let's divide this by 2. 25 minus 50. And now you can see where it's coming from. Right? This repetitive conversation so that you can see what's coming from, and I'm not just telling you. Right? You got to look at this repetitively, think about it repetitively, work with it repetitively until it's effortless for you. Right? So now, what can we say about this? Well, we can say something about rates. We just studied rates. The rate of x squared is 2x. And linear rate is constant, right? What do? We go over, up, over, up, over, up. In this case, we're doing what? Over 1 and down 10, over 1 and down 10. So what is the rate of change of a linear function? It's slope. Okay, but we're going to do that for this function over here. So x squared, we know that rate is 2x. What are we doing? We're really doubling. So if you're doubling amounts, you're doubling the rates at which those amounts occur. Think about a babysitter. You got $10 an hour. You're 8 years old, and your parents say, hey, watch little Johnny here, at least for an hour. Oh, we'll double it. You don't do it for 10, we'll double it. We'll give you $20 an hour. Right? So multipliers factor into rates. So we can double that rate. And that rate's at 20. And what did we say about the minimum? I think we said the slope is 0. And this is a statement about rates. Let's set it to 0. let's 4x minus 20 and let's set it to 0. Sure looks like x is 5. Oh, geez. Did that have something to do with an important value here? Must be a coincidence. Yeah, it's got to be a coincidence. Yeah. What can I say? It's a coincidence. Let's just look at the general situation. All right, because it's got to be a coincidence. So it looks like the slopes, if you put a couple of x's that are close together, x1 and x2, like 0.1 apart, and you do slope at one of those instances, it seems like at maxes and mins, the slope are 0. And we know x squared changes by 2x. We just kind of saw that process, and we might have to play the video 3 or 4 times before it makes sense to you. But I strongly suggest you do that before you get to calculus. That is, if you want to understand calculus. Oh, an a term. We're saying a is greater than 0 here. Oh, well, then it looks like the slope is 2ax, and the slope of a linear is b. And well, you go ahead and solve that right now for x. You get x along here. See if you got the algebra 1 skills to solve that. I'm having trouble figuring out. I think addition of b becomes subtraction. I think multiplication by 2a become. God, another coincidence. Seeing minus b over 2a from a different perspective here. Another coincidence. Oh, well, gonna have to think about the ramifications of that, because it sure seems like there's something going on here. All right, maybe we can talk about it for the rest of the semester now that it's in front of us. Hope so. I know talking about things sometimes helps.